Okay, well, good afternoon and welcome to the C3 Research Exchange. My name is Kostas Panos. I'm Professor of Electrical Engineering and Computer Sciences at UC Berkeley and also the Director of C3 and the Banato Institute. So today we are joined by Dr. Richard Corsi. Richard is Dean of Engineering at the University of California, Davis. Richard has spent most of his career at the University of Texas as a faculty member, department chair, and endowed research chair in the Department of Civil, Architectural, and Environmental Engineering, and as a member of the institution's prestigious Academy of Distinguished Teachers. Dr. Corsi is an internationally recognized expert in the field of indoor air quality, with a specific interest in physical and chemical interactions between pollutants and indoor materials. During the pandemic, he has delivered numerous national webinars on layered risk reduction to reduce the spread of COVID-19, completed modeling to underscore scenarios of high risk, developed educational tools for school districts, and conceptualized a highly effective new air cleaner for respiratory aerosols that has become known as the Corsi-Rosenthal box. He was inducted into the International Society of Indoor Air Quality and Climate's Academy of Fellows in 2008, and is past president of the Academy. He's currently chairing a National Academies Committee on health risk of indoor exposures to fine particulate matter and practical mitigation solutions. So it is my great honor to welcome Dean Corsi today and his talk, Pandemic Engineering, Accessible Tools for Lower Risk and Spread of Infection. Richard, thank you so much for joining us.
Yeah, thank you so much, Kostas. And it's an honor to be speaking with all of you today. That was a wonderful introduction, Kostas. Thank you. I would just summarize, maybe I could summarize that as by saying, the guy who's speaking today is really old. So I've been around a long time working in the indoor air quality field for about 3 decades. And I'm excited to speak with you today about pandemic engineering. Those are 2 words that I think should go together more. There were many of us that early in this pandemic, as engineers, as building scientists, as those that understood engineering controls and aerosol particles, tried to have a voice and get the word out that this looks like it's an airborne infectious disease. Unfortunately, we were not very effective in doing that early on, and I think the world has suffered for that. The lack of engineering contributions, certainly at the beginning phases of this pandemic, but also throughout to a large extent. The other important words in my title are accessible tools for lowering risk and spread of infection. So my presentation today will involve about half the presentation is kind of on the ABCs, the fundamentals of how respiratory aerosols get from an infector into a receptor. And then the second half is going to be dealing with accessible tools and how we can help people reduce their inhalation dose to aerosol particles. So, I want to start by explaining to you why I am motivated to study indoor air quality and why I have been for the better part of my career. And the numbers on the left that you see, I consider to be the indoor air quality code. All of these numbers have units of years. I'm not going to ask you to guess at what the numbers mean, but I'll just tell you that before the pandemic, the average American lived to be 79 years old on average. Women a couple of years more and men a couple of years less. The pandemic has dropped that number down to about 78. But before the pandemic, Americans lived on average to be 79 years old. We spent about 69 of those 79 years domiciled inside of buildings. In fact, we spent a greater fraction of our lives inside of buildings than most types of whales spend submerged below the surface of the ocean. Think about that. 54 of our 79 years we spent inside of homes that we live in during our lifetime. 54 of our 79 years of life inside of homes. So homes end up being a really important environment with respect to exposure to lots of things, including air pollution. We spend 26 of our years of life lying horizontally on a mattress with our face and mouth pushed up against a pillow filled with polyurethane foam as we're inhaling toluene diisocyanate coming out of the foam. We spend 6 total years of our lifetime outdoors and 4 total years of our lifetime inside motorized vehicles of some sort. People on the West Coast think that they're different and they spend more time outdoors. If you look at human activity patterns for different regions of the country, we don't. We're pretty much the same as somebody living in Omaha, Nebraska. So these are the human activity patterns that we all tend to follow. And because of the amount of time we spend indoors, study after study shows that the indoor environment affects our health. It affects our productivity at work. if we have poor indoor air quality, and it affects children's ability to learn in schools if schools are not properly ventilated or they have other indoor air quality problems. Our exposure to most air pollutants during our lifetime is dominated by the breaths that we take while we're inside of buildings. And that's true for air pollutants of both indoor origin, but also outdoor origin. All that stuff that we think of as outdoor air pollution, we predominantly breathe inside of buildings. As an engineer, as a building scientist, this thrills me because it means that we have this great opportunity to reduce human exposure to air pollution by virtue of how we build, construct, operate, and maintain buildings. And we haven't really looked at buildings in that way ever. And we need to start looking at buildings more in terms of what we can do to improve health, productivity, and learning inside of them. There are a lot of differences between indoor and outdoor environments. I don't want to dwell on all of these at great length in the interest of time. You can see many of them here, but the ones that are most relevant, I think, to the pandemic, I've circled here. One is we certainly don't have as much sunlight indoors as we have outdoors. Outdoors, we have much greater dispersion of pollutants from a source, so they mix away much more rapidly, they disperse more rapidly. The density of people indoors tends to be much, much higher than it is outdoors. And on the right in the box here, you'll see the density indoors versus outdoors, and these are densities per 100 square meters of habitable land on Earth. The human density is about 0.012 humans for every 100 square meter. Portland, Oregon, as a mid-sized city, is about 0.13 per 100 square meters. U.S. home, about 2 per 100 square meters, and a classroom, 30 to 40 inhabitants per 100 square meters, right? So that means greater density means greater physical location relative to infectors, those who might be infected. And then while it's not really relevant, the outdoor environment to control technologies for COVID-19, it is for a lot of other pollutants in the sense that we can control the indoor atmosphere and remove pollutants much more effectively indoors than we can outdoors. So this is where the story of COVID-19 starts for me. Before the pandemic, literally about 2 months before the pandemic, I was reading a paper published in 2016 or 17 by the group of authors you can see here that were talking about drivers of airborne human-to-human pathogen transmission. It's a great paper. I really, really, really encourage you to read it. But there was a paragraph in this paper, and I've circled the key here to this paragraph, talking about coronaviruses, et cetera, up above, the specter of future pandemics with unprecedented health and economic impacts if these pathogens gain the ability to spread efficiently between humans via the airborne route. This paper came out just a couple of years before the pandemic and nailed it. I mean, they really nailed what we're in right now. So I really encourage you to read it. In January, I read a BBC article about this strange thing that was happening in China. And I'm not saying this to take credit because I recognize things earlier than others. I certainly didn't. But the first tweet on social media I put out about COVID-19 was, this deserves the world's attention. And I think that was probably an understatement at the time. But in the ensuing 4 to 6 weeks after I tweeted that, I started collecting as much information as I could. And I started doing simple modeling. And the more I did, the more I convinced myself this is an airborne infectious disease. And like many engineers and aerosol scientists and building scientists, we were trying to scream out in any way we could to get people to pay attention to this. But those that were, really focused on the problem at the time weren't paying attention to that. In fact, downplayed the airborne infectious transmission route. And I think, as I said, we're all paying for that now. So some ABCs about airborne infectious transmission. First of all, the viruses we're dealing with are embedded in particles. They don't fly around naked. I still see things on social media and even in articles that talk about, filtration is required for particles of 0.12 microns, roughly the effective diameter of a virus. And that's not the case. Viruses basically use particles that come out of our respiratory system as their Uber or Lyft, as their rideshare. And those particles are essentially mucus and saliva and all the salts, et cetera, that are contained in those. We do think, and I'll get to this in a moment, we don't think, I know now that aerosol particles that stay suspended in air dominate transmission. and that we know that the virions, or infectious viruses in those particles, do decay to some extent over time, but that decay is lowest at sort of mid-range humidities. So at low humidities, the virus sustains itself longer. At high humidities, longer. At mid-range humidities, we get our maximum bang for the buck in terms of decay or inactivation of the viruses. But that decay rate works out to be about 0.6 per hour, right, in a typical indoor environment. And you can compare that with typical ventilation rates for a poorly ventilated home up to, say, a classroom or office buildings in the upper range. And you can see that we're not talking about the virus decaying so fast in air that it's going to be gone, especially, quickly, especially with respect to the timescales for ventilation and removing particles from the air. And certainly there are special cases like isolation rooms in hospitals and commercial airliners that have much higher ventilation rates. So the point there is that the decay of the particle in indoor air is really not that significant relative to other removal mechanisms. Again, the virus itself is pretty small, but it's embedded in particles that tend to be much larger. Particle diameters that carry the virus are obviously greater than the virus itself, and the particle volumes tend to be much greater than the volume of the virus. So a 1 micron particle, a very small particle that stays suspended in air a long time, has a volume about 600 times that of the virus. A 10 micron particle has a volume that's about almost 600,000 times the volume of the virus. So individual particles can actually convey a lot of viruses if there were enough viruses in the mucus and saliva in an infector when they're coughing or speaking. Particle size is important for all the reasons that I show here. It's important in terms of the fraction of the deposit on surfaces. It's important in terms of removal and filters and mass, deposition in the human respiratory system, how much and where it deposits. And this is just an image from an EPA website that shows the cross-section of a human hair, which tends to be 50 to 70, maybe up to 100 microns, depending on how coarse your hair is. And then you can see circling that particles that are 10 microns in diameter. These are these blue beads, and then superimpose on the blue beads particles that are 2.5 micron in diameter. So you can see how small the particles are that make up suspended aerosol particles in the indoor environment, which we think is the most significant types of particles for transmission of for COVID-19. So the exposure pathways that we would sort of typically look at for infectious disease, there are others, but these are the main ones we've focused on during this pandemic, are direct contact. You shake hands with somebody who just wiped their nose or sneezed into their hands. Fomites, these are particles that are deposited on surfaces that we touch and then touch our eyes or our mouth or our nose. Close contact, where we can have large particles, ballistic particles that don't stay in air very long, but also concentrated aerosol particles, particles that do stay suspended in air. They're going to be most concentrated when you're near an infector. And then what I call the far field, which is just the accumulation of particles in an indoor space, respiratory aerosol particles that may be virus laden. And so somebody who's well away from an infector may inhale those particles. And then there's these disruptors in the system you can see here. So, ventilation changes the power input to the space, causes greater mixing, reduces the concentrations in the far field, and can also cause greater dispersion in the near field. The same with portable air cleaners, the same with mechanical systems. These things disrupt not only what's in the far field, but also the nature of the mixing and dispersion, and therefore the concentration in the breathing zone of somebody in the near field. From all of the outbreak data, all of the experimental data, all of the modeling that's been done to date from the start of this pandemic, everything points to respiratory aerosol particles as being the dominant exposure pathway for people that get infected with COVID-19. And I want to note here, at a free stream airspeed of 5 centimeters per second, a 5 micron particle can travel over 300 feet in indoor air before depositing on surfaces 1.5 meters below. At the beginning of this pandemic, there were a lot of people telling us that nothing over 5 microns gets beyond 6 feet. I don't know where that came from. It defies the laws of physics, but 5 micron particles can stay airborne for a long time, as can 10 micron particles. And data also indicate now that the highest viral load for people infected for COVID-19 tends to be in particles in the 1 to 4 micron range. So we're talking about particles that stay suspended in air. I wanted to say something about the UC system. So, UC Davis used to be the university farm during the Spanish flu. And I found this article from the University Farm student newspaper from 1918 during the Spanish flu that actually described experiments. We don't do these things anymore, but an experiment where a graduate student washed his throat with a germ-laden liquid and then stood at the end of a table and talked to in an ordinary tone and then in an elevated voice. And the germs were collected in bowls spaced out across a 12-foot table. And what they found was that particles went all the way across the table, the 12 feet of table, and probably would have been collected much further for the reasons that I just mentioned. But I thought it was interesting at the end of this article, the moral of the article was wear your mask, right? So Aggies and those in the University of California system understood back during the Spanish flu the importance of reducing respiratory aerosol emissions from those that are infected. So in the indoor air quality field, sort of rule number one is to reduce the source or remove the source. Famous quote in our field, if there's a pile of manure in a space, do not try to remove the odor by ventilation, remove the pile of manure. That's Max von Pettenkofer in 1858. What we're trying to do here is to get rid of the emission source. In the case of COVID-19, that means testing and isolation and not going to work if you feel any symptoms. Those are the ways of reducing the number of infectors in a space, removing the number of infectors in a space, so completely doing away with the source. But we can also reduce emissions. But to reduce emissions, we have to understand the nature of emissions, right? And by the way, in this simple, well-mixed system that's steady state, the denominator here are sink terms: ventilation, deposition to surfaces, and engineering controls. V is the volume of the space. So the main emission sources here are breathing. Just by breathing, an infector emits respiratory aerosols. Speaking, singing, which would be like very loud speaking, coughing, and possibly resuspension, which I think hasn't received enough attention during this pandemic. These are some experiments that we did in classrooms in Central Texas before I left UT Austin, 46 different classrooms. This is just one classroom. Every one of these black spikes that you see on over a 3-day period involve students coming into a classroom, students leaving the classroom, and students engaged in certain activities in the classroom where there's movement, there's feet movement, there's clothes movement, et cetera, where we get a resuspension of particles. These happen to be PM10 particles. But whenever that happens, if you have any freshly deposited aerosol particles that contain viruses, those can become resuspended and breathed. But I'm not going to dwell on that. We'll talk about the others for just a moment. Speaking is important. It's probably the main source of emissions from asymptomatic individuals who are not yet coughing, right? So these are experiments done at UC Davis and published in 2019 before the pandemic that show the number of particles emitted per second versus the amplitude of speaking. So this was for 5 male and 5 female subjects. There wasn't a gender difference obvious, but you can see that the number of particles emitted on a log scale is a strong function of the amplitude of the voice, right? The louder you're speaking, the more you emit. So in a busy restaurant where nobody's wearing masks and you have to speak really loud so the person across the table from you can hear, that's an environment where you're going to have high emissions where people aren't wearing masks. This was a single subject, a female subject here, so you can see how well the data actually fit in terms of particle emissions per amplitude. And here you see the number of particles per second versus particle diameter, I believe, for this subject for different different amplitudes of speaking, red being the highest amplitude, brown being the lowest amplitude. And you can see that the data are clustered here in terms of speaking emissions around those particle sizes that we do think have the highest viral load. Breathing, in general, emits about 1/10 of speaking at a normal amplitude. There has been data published on emissions from coughing events, the number of particles per cough. You can see here 9 subjects. Gray bars is during influenza, not COVID infection, and the light gray bars are after recovery from influenza. What you can see here is this huge range in emissions of particles per cough, anything from 900 to 300,000 particles per cough, a mean of about 75,000 with a pretty large standard deviation. And when you look at the distribution of particles from a cough, this happens to be, I think, from subject number 8, you can see where the particles are from, roughly 0.35 microns up to about 2.5 microns. It turns out about 63% of the total particle volume in this range comes from particles less than 4 microns. Even though their volumes are much smaller than 9 or 10 micron particles, there's just in so much abundance, that's where we find most of the volume or mass. Before I get into the accessible technologies, I want to say one more thing, and that is we need to start coming in tune with what I call inhaled deposited dose or inhalation dose. Inhalation dose is what matters when we're talking about an airborne infectious disease. Inhalation dose is the simple product of 4 numbers, right? One is the concentration of particles of, say, size I in the air. That'll be number of particles per liter of air, right? B, and we never talk about this, is the respiratory minute volume. You're all probably sitting in your chairs listening to me right now. You have a relatively low respiratory minute volume, a volume of air that you're taking in and exhaling every minute. If you left this talk and you went and did heavy aerobic exercises, your respiratory minute volume might be 10 times higher than it is right now. So places like gymnasiums are a particular concern during a pandemic where airborne infectious disease is more, because if somebody's infected and they're breathing heavily, they're going to emit a lot more. If somebody's a receptor and they're breathing heavily, they're going to take in a lot more. So B is important. T is the time and the space with the infector, and FDEP is the deposition of particles of size I in the respiratory system. What we'd like to do is integrate the inhaled dose over all particle sizes, convert the particle sizes to volumes, and come up with a total volume deposited in different parts of the respiratory system, the head region, the tracheobronchial region, and the alveolar region. From an engineering standpoint, we focus on concentration, right, in the air. So the way to reduce concentration is to lower emissions. The way you lower emissions is to test and isolate, so people that are infected are not in the space, but also to lower with the infector wearing a mask. And the only way you can assure that is if everybody wears a mask in the indoor space, right? The second is for the receptor to wear a mask. Everybody wear a mask in the indoor space, because the concentration in this dose relationship is on the inside of the mask if we're wearing a mask, which hopefully will be much lower than outside of the mask. The indoor volume and the amount of mixing and our ability to use that entire volume to dilute concentrations is another way of dealing with lowering inhalation dose. Certainly deposition on indoor materials lowers dose. If we increase ventilation, we can lower the concentration for all particle sizes. We can use engineering controls, which I'll focus on in just a few minutes, especially filtration. Unfortunately, in crowded indoor environments, my simulations show that up to 2 to 3% of the total particles emitted by an infector can end up in the respiratory systems of other people in that environment. It literally measurably lowers the concentration in those kinds of environments in the air. And the amount of time that the infector spends in the space will also affect the concentration. So leaping from emissions to reception, we do know that in our respiratory system, particles of different sizes deposit with different efficiencies. Some don't deposit and come right out on our breath. So this happens to be a plot for nose breathers doing light exercise. And you can see on the horizontal axis, the particle diameter microns and the respiratory deposition fraction for different parts of the respiratory system, the head region, the tracheobronchial region, TB, and the alveolar region, the deepest lungs. And it's important to recognize, again, that we're probably dealing primarily with particles that are kind of in the 0.5 to 4 micron range as being dominant, which happens to coincide with the secondary peaks for tracheobronchial and alveolar deposition here, with a pretty high head region deposition. If we look at a 1 micron particle, you can see that for this scenario, 1 micron particle, about 50% of the particles you inhale deposit in your respiratory system, about 50% come out when you exhale. So understanding the nature of the particles, the size of the particles, where they deposit, where most of the viruses is, and which particles we should be actually focusing on controlling to reduce inhalation dose is important. So early in the pandemic, without getting into a lot of details, it did some really simple mathematical modeling, simple ordinary differential equation for a well-mixed space, solve it, you get the equation that's shown here that shows the concentration in indoor air for different particle sizes, I, initial concentration here at the beginning of your analysis, emissions, which include breath, speaking, and coughing, and I superimpose the data from the literature in the model, volume of the space, and then beta here are these sink terms or removal terms. I focused on the far field initially, and I want to tell you that recently involved with some experiments which we just submitted in a paper for peer review that works on multipliers for near field versus far field. And I think those results are going to be very interesting to people. So I took this model and started applying it to different environments. This was a classroom environment, focusing on that particle range we think is most important. And you can do things like looking at where do the aerosols go? So here I have an underventilated classroom, which is almost 100% of all 200 classrooms I've ever studied. A classroom that's ventilated according to ASHRAE 62.1 2019 standards, an overventilated classroom relative to ASHRAE standards, and then ASHRAE standards with a portable HEPA air cleaner in the classroom. And you can see that most of the particles are removed to outdoor air by ventilation. Surface deposition becomes important as we get to lower ventilation rates. So even for these tiny 0.5 to 4 micron particles, we can start converging on 20% of the particles depositing on surfaces in underventilated classrooms where the particles just have a lot more time to deposit on surfaces. And then you can also see the impact of putting a HEPA air cleaner in a classroom, which can remove a fairly large fraction of the particles that come out of an infector's respiratory system. We can also look at where particles go, right? So in the respiratory system, again, for nose breathers here, we see most of the particles in this size range are depositing in the head region. We have about 25% in the deepest lungs, and then a smaller fraction in the tracheobronchial region. And the numbers you see at the top of each bar is the total volume of particles that deposited in the respiratory system of an individual in the classroom during one class. This was a university classroom. I think it was a 75-minute simulation, something like that. We then applied the model to a restaurant in Guangzhou, China, where we had by far the best metadata in terms of air exchange rates. There were videos in the restaurant that showed where people were and whether the infector moved or not, and how frequently the infector was speaking. Hugo Lee's team at Hong Kong University went into this restaurant and did follow-up tracer experiments under the same kinds of conditions. It was a really rich environment for an outbreak to do modeling with. And so we modeled that environment using the simple model. We estimated that the infectors in this zone of the restaurant had between 1 and 10 picoliters of respiratory aerosols from the infector deposited in their respiratory system during a 75-minute event with the infector present. The actual range depended on what we assumed about emissions and mixing. Turned out that wasn't that important, because what we basically did is we took that infector, no matter what we assumed about emissions, and we put that infector in different environments in the United States. A school classroom, a university classroom, a gym, a restaurant, a ride share, right? And we started doing simulations saying, if we find environments where we have this much deposited in the respiratory system of people in those environments, that's probably an environment we should be concerned about. We found pretty high levels, numbers of picoliters, certainly in this range, for choir practice. Remember Skagit? We simulated that, said that was a bad environment. We simulated gyms where there were outbreaks. We got ratios of that situation to restaurant X in Guangzhou that were greater than 1 in that gym. We simulated a lot of those kinds of environments, and we were able to predict with this simple model, right, environments where we go, oh yeah, that was a bad environment to be in. And conversely, we can say these are bad environments to go into in the future. We superimposed on the model for how much gets into respiratory systems a dose-response relationship for a human coronavirus, which we believe was closest to SARS-CoV-2, right? And this dose-response relationship for HCOV229E is shown here. And it gives the response probability, which means infection fraction, versus the average exposed dose. And think about this in terms of total virions or infectious viruses, plaque-forming units that deposit in the respiratory system. And we took that for the information that we had from the Guangzhou restaurant in terms of the percent that were infected and the total volume in the respiratory systems. And we were able to link volume to virions for that infection event. And it turned out to be about 3 virions per picoliter of fluid, of particles that were deposited in the respiratory system. And then we took that and we started applying it to a bunch of other scenarios: outbreaks on aircraft, outbreaks on buses in China, the Skagit choir event, and so on and so forth. And we were actually able to reasonably predict the number of infectors in those spaces. We said, why should this be our tool? And this is where accessibility comes in. At this time, schools were struggling with what to do. And they were doing a lot of bad and wrong things by purchasing technologies they probably shouldn't have purchased and spent a lot of money on. So wanted to make this an educational tool for schools that showed the benefits of layered risk reduction, respiratory deposition and risk, and accounted for a lot of different factors that you can see under the factors here. And we basically make this available for free. And you can go to this right now and just type in safeairspaces.com and you can play around with it. There's some little strange things with it. So the software that was used doesn't allow lowercase letters. So you see, meter squared is capital M squared, but you get the picture if you actually do it. So I developed the mathematical backbone for this and had some great colleagues at the University of Oregon who superimposed the dose response relationship and put this wonderful user interface on it for school folks to use. And this is what it looks like. I'm not going to run it now. I'm just going to show you 4 quick slides. The interface for this shows you, allows you to input all these parameters for a classroom or other environment. It converts all the metric units to English units for those in the US. It shows the net results of the number of infections. The donut here shows you where the particles go, how much is vented to the outdoors, how much is deposited on surfaces, how much deposits in the respiratory systems of individuals, in the collective respiratory systems. It shows you a human respiratory system and where the particles are depositing, gives you a time profile for the buildup in the classroom. And then the thing that everybody loves is this thermometer that shows you sort of the degree of infectiousness of the environment. And what we did here, and this is based upon that dose response relationship that I mentioned to you. So what we do here is when you input your data, this happens to be for a classroom that's underventilated, 2.5 hour exposure, not a full day. So this could be a university laboratory, for example, lab class, underventilated. So starting off about half of the ASHRAE standard, no masks, and a high emitter in the indoor environment. All right. And what you can see in that case is this black dot says you're in a classroom or you're in an environment of extreme risk, right? And again, this model was quote unquote validated with a number of different scenarios in the literature. So then we asked the question, well, what if suddenly we want everybody to wear masks? So everybody wears a pretty crappy mask. So these masks are less than 40%, almost 40%, for less than 40% efficient at removing particles that are emitted and removing particles in your breathing zone. We can do much better than that, obviously. And you can see just by everybody wearing pretty lousy masks, we get from extreme risk to the borderline of high risk and moderate risk. The power of that is to tell people the importance of masking. You can see it visually, and a lot of people have commented that that visual observation of that black ball dropping is really powerful to them, right? So in that particular case, we get a 62% reduction in risk, less infections during the 2.5 hour period. Then we say, what if we increase ventilation? Now we go beyond ASHRAE 62.1 2019, and we can drop from the low end of extreme risk all the way down to the low end of moderate risk. Now we have uniform lousy mask wearing and increased ventilation, and that black ball drops further. Now we're at 82% risk reduction. And then on top of that, if we basically say, let's put a good right-sized HEPA filter in the classroom and take a 20-minute mask break in the middle of this 2.5 hour class event to allow the room to purge itself of what was there and allow everybody to come back in, we drop that black ball all the way down to very low risk category. Still some risk, obviously, but remember, we're starting with a very high emitter. And so if it's not a high emitter, we're almost at a very close to zero risk in this environment. You can see with the HEPA air cleaner in place that it removes about 50% of the particles that are emitted by the infector in this case. So you can see the value of putting in a $300 right-sized HEPA air cleaner. And that moves me into the last segment of the presentation, which is accessible technology, starting with a portable HEPA air cleaner. I want to say this from the start, that portable HEPA air cleaners are proven technologies. If they're right sized, they can really reduce the amount of respiratory aerosol particles and other aerosol particles in any kind of indoor environment if they're right sized. They're great for supplementing ventilation when you're unable to increase ventilation. Valuable in wildfire season where you don't want to increase ventilation, but you want to make sure that you clean the indoor environment, even when you have lower ventilation. And you can get significant dose reduction. A key parameter is called the clean air delivery rate, or CADRA. And on a good HEPA air cleaner, on most HEPA air cleaners, you'll go online or you'll find it in the store. It'll actually list the AHAM certified clean air delivery rate for tobacco smoke, dust, and pollen. And typically with HEPA air cleaners, all those numbers are going to be very, very similar. 300 cubic feet per minute is a pretty good clean air delivery rate, which is equal to the fraction of particles removed in one pass through the air cleaner, single pass, multiplied by the volumetric airflow rate of air through the air cleaner. So single pass removal fraction times the airflow rate, typically in cubic feet per minute. So the way we can use that number, the clean air delivery rate, is to convert it to an equivalent air changes per hour. What that means is, how good is that air cleaner in terms of, if I use it, it's equivalent to increasing the amount of outdoor air I bring in, clean outdoor air I bring in, with respect to lowering aerosol concentrations. Okay, same bang for your buck, essentially, or same removal effectiveness. So you take the clean air delivery rate and you divide it by the volume of the space, assuming it's a well-mixed space. So an example, if we have a 600 square foot classroom, that's a pretty low ceiling, so an 8-foot ceiling, that gives us 4,800 cubic feet. If I have a clean air delivery rate for my HEPA air cleaner of 300 cubic feet per minute, I take 300 cubic feet per minute, and I'm going to actually 300 cubic feet per minute divided by 4,800 cubic feet. That gives me 0.0625 per minute. If I multiply that by 60, I get 3.8 per hour. If I plug this into a simple equation that shows me the steady state, well-mixed concentration in the indoor space, let's say I start with 2 air changes per hour in a classroom. Deposition of surfaces is negligible, say for the small particles we're dealing with. If I have initially 2 air changes per hour down here, or 2 per hour, I add to that 3.8 for my HEPA air cleaner. That gives me 5.8 now in the denominator. That leads to about a 66% reduction in aerosol concentrations in that classroom space, right? So we get these significant benefits from a HEPA air cleaner. The problem with HEPA air cleaners for the general public is that they're cost prohibitive. These range anywhere from $275 to $900, depending on who you buy your HEPA air cleaner from. And so I stayed up late one night saying, obviously a lot of Americans live paycheck to paycheck. HEPA air cleaners are just not accessible to a large swath of Americans. How do we create something which can be perhaps almost as effective, maybe as effective as a HEPA air cleaner, but at a much lower cost? And I did see that some people during wildfire season were promoting putting a single filter on a box fan. So that was not my idea. People were already doing that. And it was primarily for wildfire season. I had concerns about this design, even though people were reporting for relatively low spaces, like an 80 square foot home office or other relatively small spaces, were showing some pretty good reductions in fine particle concentrations. I did have concerns about the resistance to flow. You put a single filter on a box fan, and that's going to put a lot of work on the motor. So it's going to be wear on the motor. Resistance to flow, lower flow rate means a lower clean air delivery rate, because remember, that's one of the 2 things we multiply together to get the clean air delivery rate. And also frequent filter changes will be necessary. So scratching my head late one night as an engineer, I said, how do we make this better, right? So I want a larger surface area to lower the resistance on the fan motor so that I can get a lower overall air speed, which lowers the resistance, lowers the head loss for engineers that do fluid mechanics. And also maybe I get a higher airflow rate because of lower resistance, even though my air speeds are lower, right? That was kind of my goal. If I get a higher airflow rate and lower air speeds, I should get greater clean air delivery rate, as well as a lot less wear on the motor of the fan. And I'll have to change the filters less frequently. So my first thought was, well, we could arrange these filters, maybe 3 or 4 filters in parallel and build a plenum for them. And then thinking about that, that's not something that most people are going to have the room to put in a school classroom or their home. That would be a big, bulky thing, right? So just a little more thinking said, well, we can do this in a box arrangement, right? We can get the same surface area in a smaller volume by making the air cleaner walls itself the filters, right? And so that was the idea. And I wanted this to be open source. So threw it out on social media, did some interviews with some magazines. There are websites now that talk about the Corsi-Rosenthal box and how to build one out of MERV 13 filters with a box fan and a shroud around the outside of the box fan to improve the airflow distribution, the airflow rate. This was actually an engineer in Canada's idea after I threw the idea out to improve that. And it does, it increases the flow rate by about 10 to 15%. Jim Rosenthal, the day after I put this out on social media, he's an old friend from Texas, and he built one that night and put it out on Twitter the next day. And so this was the first Corsi-Rosenthal box. And it looked beautiful to me. I thought I would buy that in Home Depot. That's really nice looking. And it turns out that you can build something like this for anywhere from about $60 to $90, depending upon the cost of the filters, where you purchase them. If you purchase them in bulk, you're going to build multiples, 4 or 5 of these versus a single unit. So we're talking about a third to a quarter of the cost of the lowest cost, very good HEPA air cleaner, and about 10 to 15 times lower than some of the more expensive HEPA air cleaners. So then the next question is, do they work, right? They should if you use MERV 13 filters, because as you can see right here, MERV 13 filters have pretty good removal effectiveness. Theoretically, the brown curve here is MERV 13. For particles in the size range we're interested in, even if we go down to 0.5 microns, we're talking about 50 to 60% removal effectiveness. But at a very high flow that we can get with a box fan, we're going to have flows that are much higher than those that go through HEPA air cleaners. So when you look at the clean air delivery rate, which is the efficiency times the flow rate, we might have something here in terms of an effective device. And at UC Davis, we've just had Chris Kappa's team has just had a paper accepted. It's been through the review process. It'll be the first paper that really details a true effectiveness of Corsi-Rosenthal boxes and compared those in a classroom and home office versus 2 different HEPA air cleaners. One HEPA air cleaner had a rated clean air delivery rate of about 300 cubic feet per minute. And you can see that the experimental design was good because that's exactly what the team got, about 300 cubic feet per minute. And the other one, 100 cubic feet per minute. And you can see that's pretty much what the team got. So that kind of validates the methodology used by the team. But look at the Corsi-Rosenthal box here. Low setting of the fan, medium setting of the fan, high setting of the fan, above 800 cubic feet per minute in clean air delivery rate. 2.5 times a HEPA air cleaner that costs 4 times as much, right? You can also see on here power draw for the different air cleaners and sound levels 1 meter away from the air cleaner. So this paper has been accepted. It should be coming out officially soon. And I'm really proud of the team that did this research. And it really proves that this is not just a low cost and accessible technology, but an incredibly effective technology. As some context, if you apply 800 cubic feet per minute as a clean air delivery rate to a dorm room where students are spending a lot of every evening with their masks off in the same room with 1 or 2 other people, a high-risk environment where infection can sweep through dorms, and you take a standard dorm room, a standard-sized dorm room, and you apply the same equation I showed you previously, we can get an equivalent air changes per hour of 24 per hour. 24 air changes per hour with a Corsi-Rosenthal box in a dorm room. In a classroom, a 700 square foot classroom, which is a reasonably sized K through 12 classroom with a 9-foot ceiling, doing the same thing, we can add an equivalent air changes per hour of 7.6 from the Corsi-Rosenthal box to whatever the actual ventilation rate of the classroom is. Typically for ASHRAE standards and typical classrooms, that's 2.5 to 3.5 per hour. That gives us 10 to 11 air changes per hour. As some context, typical air changes per hour by design for isolation rooms in hospitals where people are infected and we put them under negative pressure, the rooms, is 12 air changes per hour. So I can turn a dorm room with the Corsi-Rosenthal box into a super isolation room in a hospital to protect kids in the dorms. The same thing for a classroom environment. we can almost make the classroom environment equivalent to an isolation room in a hospital. It also helps with the time to 95% decay of particles. If kids leave the classroom and they leave for 45 minutes to go to lunch and they come back in, we want to purge that classroom of whatever accumulated in the classroom air. And this shows the time to 95% decay versus essentially the equivalent air changes per hour on the horizontal axis. Remember I said in one example, we're starting with 2 per hour in a classroom. That tells me about 90 minutes to purge out most of the aerosol particles. If I can increase that to 12, I'm off chart, or 11, I'm off chart. It takes 15 minutes. And in a dorm room, it takes about 5 minutes. If you have somebody who's infected that leaves, and then the other person comes back in, if the Corsi-Rosenthal box is on, it purges that room in literally minutes. So again, real benefits. Underwriter Labs has done tests on the Corsi-Rosenthal box under probably worst case scenarios and found that it's safe. There's no fire hazard, there's no temperature burn hazards, et cetera. And those results have been published. So I'm going to go through a bunch of slides real quickly now because I think we're almost out of time, but I'm just going to glance at each one of these slides to tell you how exciting this is to me. Media attention. So CBS Evening News did a story last fall on the Corsi-Rosenthal box with Jonathan LaPook. This really generated a lot of attention and people really started thinking about building these for their kids' classrooms or their own homes. The BBC did a story on Welsh schools building these strange homemade jerry-rigged air purifiers. Smithsonian Magazine, just over a week ago, has a story on the homemade air purifier that's been saving lives during the COVID-19 pandemic. 3M just tested a bunch of Corsi-Rosenthal boxes and came out with a story that said, hey, this stuff's legit. It actually works. We can save lives. Some examples of citizen engineering. It's not just STEM, it's STEAM. People are making these, posting them on social media, turning them into snowmen and other things. My favorite down here is somebody who built one and turned it into an old-fashioned turntable where the fan itself is the LP and a straw connected to the switch on the box fan is kind of the needle. But you see everything from psychedelic to really professional designs here. More look very professional. This person is putting a barcode on it that people can, take a picture of with their phones, and it tells them how to build more of these. Here are more being built. These are being built and sent out to K through 12 schools in this area. Really professional looking units that people are building. The wooden one is fantastic. Here they are being built in bulk and handed out to K through 12 schools by one organization. You see them lined up in a gymnasium here. People are posting these when they see them in the wild. So here's one in a hospital in, I think it's Australia or New Zealand, I'm not sure, but they took a picture of a Corsi-Rosenthal box in a hospital, one in an organic grocery store. One person found one at a gym that they go to. So these things are really spreading like wildfire. Here's one that somebody took a picture of in a place where their choir gets together to sing. There are 2 Corsi-Rosenthal boxes here. And the thing that thrills me is the educational opportunities that come about from this. For what I just continue to say is citizen engineering, right? Teaching kids about what an aerosol particle is, what particle sizes are, what units we use, what airflow rates mean, what a filter does, how it does it, how we can get a clean air delivery rate by multiplying 2 things together. And they have fun building these units. And I've had actually parents contact me saying that the biggest thrill they got was when their child plugged one of these things in and felt the airflow coming out the top of it. This image is of an engineer at UC Davis and Ph.D. student Teresa Pistaccini working with students at a junior high school in Sacramento building Corsi-Rosenthal boxes. These are high school students in Pennsylvania building Corsi-Rosenthal boxes. In New York City, building these boxes for their own high school. This is an entrepreneur, a 14-year-old entrepreneur in Mississauga, Ontario, just outside Toronto, who is actually taking money from people for the cost of materials only, right? So he's saying, you pay for the materials and I will build you one of these. And he's been delivering these around Toronto. And I actually contacted him personally and I encouraged him to apply to UC Davis in 4 years for our College of Engineering. I mean, it's just thrilling to see young people getting excited about this. Brown University has built, I believe, 2,000 Corsi-Rosenthal boxes for their own university. This is Marina Creed, who's a professor of nursing at the University of Connecticut, who's literally building these with her students by the truckload, as you can see here, and distributing these to schools, K through 12 schools in her area. UC San Diego has built about 250 to give out to local schools. Here we have a professor of epidemiology at Arizona State University has her students building Corsi-Rosenthal boxes, and they've delivered them to schools across the Valley of the Sun around Phoenix. This is one of the school teachers who received her box and hopefully is happy about having it in her classroom. We had a contest at UC Davis where we had freshman and sophomore students building these, and we gave awards for the best designs. Most of these students live in the dorms, so they could either use their boxes for the dorms or donate them. And then we get down to small children who are building these and, learning about them on the whiteboard and building them themselves. This is a fourth grader in Hawaii who made a YouTube video about how she built her Corsi-Rosenthal box. And I really encourage you to watch this. I can't tell you how much it warms my heart to see this. Even kids that are pre-kindergarten building these. Children in Wales and their teacher. And that's it. And I just want to say, I've done a lot of research during my career, spent a lot of taxpayers' money, published a lot of papers. This idea came out of one night of brainstorming and throwing it out as an open source concept. And it's taken the world by storm. And it's probably the most significant thing I've done during my career. And I didn't spend any taxpayers' money doing it. Technology for the greater good is important. It's important that engineers keep that in mind, that it's possible that if we put our minds to it, we can work to leave nobody behind and to leave no community behind. And we ought to be doing more of this kind of thing to help all of society, not just some of society. And I think citizen engineering is a concept that we should be pushing more and more and more. So I'll end there, and there's links here if you'd like some additional information. Thank you.
Thank you. Thank you, Richard. That's tremendously inspiring. We have several questions already on the Q&A tab. Maybe you can see them directly. Maybe you can take a stab at those in the few minutes that we have left.
Yeah, I have to unshare my screen if that's okay, and I'll take a look at the chat.
It's on the Q&A, not on the chat.
Oh, okay, Q&A. Thank you, Costas.
Yeah. So one of them is about how many air changes per hour would be recommended. I understand that depends on quite a bit of context.
Sure. So obviously, the higher the better. Equivalent ACH. We'd like to, the number 6 has been batted around a lot by some, saying we should at least achieve 6. I think that's out of frustration that in many schools we're operating at about 2 or 3, and the idea is to at least double where we are now as a practical means. I think we can get much higher than that with the kind of technologies that I talked about today. The higher the better, right? From my perspective is aim for an isolation room in a hospital. And if you get close to that, you're doing really, really well. Yeah.
Richard, I have scanned the questions, and let me just prioritize one kind of arbitrarily because it looks very interesting to me. When it comes to school districts adopting these technologies, are there going to be safety and regulatory issues that we need to overcome, or is it just a movement? Can you comment on that?
Yeah, so that's a great question. And the answer is that some school districts have been very, very open to this. I think they see it as a learning experience for their students, but also as a very low cost way of keeping the environment cleaner. And then other school districts have been raising all sorts of issues. Those school districts say there's safety concerns, it hasn't been tested, it might catch on fire. So when we see things like Underwriter Labs doing tests on them and saying, this is completely safe, we've been trying to get that information out. But there are still resistant school districts. I will also tell you there are resistant school districts that have spent a lot of money on technologies that I will not name that are, for all intents and purposes, not effective. So they're using a lot of their resources to purchase something that doesn't come anywhere close to this cheap technology that we could use to make the classroom safer.
How would you recommend a schedule for filter changing?
It's a great question. So part of that depends upon how dirty the environment is. What I'm starting with is a standard, and this is based upon running these things myself for some time. I actually have one outside of my office. And, you know, in theory, as an engineer, I'd say I want to measure the pressure drop across the filter and make a decision based on that, but people aren't going to do that. So they just want a time frame. So for me, it's sort of 6 months as a starting point to change the filters. People do get concerned because they start seeing the filters discolor, but that's natural for filters, even when you have small numbers of particles on them. You don't want the cake to get so thick that it changes the resistance and your airflow rate changes, but 6 months is reasonable in an environment that's not super dusty and dirty. It may be that in a very dirty environment, it ends up being 3 or 4 months, and in some environments, it might be longer than 6 months. But I would go with, you know, if you built one of these during the beginning of the school year, you'd probably want to build another one somewhere halfway through the school year.
A question that is related to that, I understand that you might get out of the low cost objective. Would you comment on air ionization as a technique? Some people ask.
Yeah, so the problem with ionization technologies, well, there's two concerns that people have. And I want to be careful about what I say, because I do believe that technologies can be improved. So one is the question of how effective they are. Go back to the 1990s, a lot of people were buying ion generators it was all the craze. The number one air cleaner in people's homes was an ion generator. Don't need to mention what it was, most people remember it. They were marketed in a very slick way as being quiet, okay? The reason that they're quiet is that they have very little flow going through them. So even though they were really efficient, they had a high single pass removal fraction, so little air went through them that they had a very low clean air delivery rate relative to something like a similarly priced HEPA air cleaner, right? There are new ionization technologies since then. Some of those have been tested by researchers and published in the published literature, in peer-reviewed literature, that show that they may not be very effective at all at removing virus-laden aerosol particles from air. And the other issue that's been brought up is that they do engage in some indoor chemistry that leads to reaction products that are formed that contain oxygen, so they're reactive oxygen species, and that can lead to potential health effects. Although I haven't seen any data to prove that. I would focus more on whether they're effective or not. And I just think there hasn't been enough in the peer-reviewed literature from proponents of ionization technologies that convinces me that they can be effective. But I'm going to leave that open-ended.
Yeah.
So,
indeed, there are several more questions, but we are on time. So I would like to thank you, Richard, for an amazing presentation and a very inspirational story. I hope that some of these questions could be asked via email. Maybe you can contact Richard directly, and I'm sure he'll be glad to respond to those. So thank you very much for attending today's Research Exchange, and hope to see you in the fall.